Okay, Assalamu alaikum everybody. First announcement, we will delay the quiz to after the break, Tuesday after the break, and it will be on chapter 27. We'll try to finish chapter 28 this week. Okay, I will also post the homework for this chapter 28. It will be due in the week after the break, inshallah. So let me remind you of what we have covered so far. And unfortunately, yesterday I found that the video was not recorded. So anyway, so we missed the lecture. So remember, yesterday we said magnetic fields can be either generated by a permanent magnet or by passing a current through a wire, and we will see how we can do that. And if you have a permanent magnet, it's made of material that causes, for example, iron to be attracted to it, and the permanent magnets, they have a north and a south pole. Okay, and we said if you have iron filing and you put it close to a permanent magnet, you will see these irons will distribute in such a way to really show you the electric field line, the magnetic field lines. So like we represented electric field lines to indicate the direction of the electric field, we also can use magnetic field lines in order to represent the direction of the magnetic field. Okay, and also the number of lines per unit area indicates the strength of the magnetic field. Okay, we said also that the magnetic field lines, they always go out of the north pole of a magnet towards the south pole of the magnet. So the direction is always from the north to the south pole. So as you can see here, we are drawing the magnetic field lines. Okay. We also mentioned that the opposite magnetic poles will attract each other. So if you bring a north to a south pole, they will attract each other. But if you bring north to north pole, if you have two bar magnets, they will repel each other. And if you bring south to south, they will also repel each other. Okay? And we spoke about the Earth, and we said the Earth magnetic field is shown here by illustrating the magnetic field lines. And we said the Earth magnetic field is very important. It protects us from the cosmic rays and is also very important for navigation. Without it, it's difficult to determine the directions. Okay, and finally, we illustrated that physicists performed experiments on the motion of charged particles in a magnetic field in order to determine the very important relationship that we introduced last time, which was that the force, magnetic force, if you have a charged particle moving at a velocity v, and in a magnetic field B, let's assume it's a constant magnetic field, then it will experience a force that is given by Q V crossed with B. So this is the vector cross product. Okay, and so the magnitude of the force is given by the absolute value of the charge Q times the magnitude of the velocity, which is the speed, times the magnitude of the magnetic field vector B, times sine the angle between the velocity vector and the magnetic field vector. Remember, the angle has to be the smallest angle of the two angles of the two vectors are making. And we said the direction is obtained with the right-hand rule. So you point your first vector, which is the velocity vector, in the direction of your index finger, and the second vector, which is the magnetic field vector, along the middle finger. Your thumb will be pointing in the direction of the force. That is, if the charge is positive. If the charge is negative, we said you have to reverse the direction. So the charge, the sign of the charge does affect the direction of the force. Okay? We said the unit for magnetic field is Tesla, and Tesla is Newton second per Coulomb meters. Okay? And we started solving some problems. We mentioned some very important properties, and we said because the force, magnetic force, is always perpendicular to the velocity and always perpendicular to the magnetic field vector, it does not do work. It does not do work because the displacement is always perpendicular to the force. Okay, hence the magnetic field, the magnetic force does not change the speed of a particle. It changes the direction of the velocity vector, but it does not change the speed, and it does not change, since it does not change the speed, it does not change the kinetic energy. And we compared electric force with magnetic force. These are very different forces. The electric force acts on a charge whether it's moving or not. The magnetic force, if the charge is not moving, there is no force. Okay, so if V is equal to 0, there will be no force. And we mentioned some other important differences between electric force and magnetic force. Okay, we started solving some problems, and we did this problem, and in this problem we just used the force, the magnitude of the force is Q VB sine of the angle. We did the same thing in this problem, and for this problem we used the matrix method. Okay, we illustrated the matrix method, and remember we said F is Q V crossed with B. You can put the I and you can write the charge. In this problem we have the charge is minus E, which is the charge of an electron. Then in the matrix you should not remember that we have a minus sign here for the J vector, and so you multiply the I vector times this matrix, okay, the minus J vector with this matrix, okay, and the K vector, you multiply it with this matrix, and you get the components. All right, so this is what we have done last time so far. Okay, you can also solve this problem by not using the matrix method. For example, if I can write F is equal Q, which is minus E, V crossed with B, V is 2 10 to the power 6 I plus 3 10 to the power 6 J crossed with the B vector, which is 0.03 I plus 0.15 J. Okay, so I can start do the cross product between I, and so these are two parallel vectors, so it will be 0, so this will be minus E. Okay, so if you do the 2.6 I times crossed with 0.03 I, it will give you 0, because these are I crossed with I is 0. Then you do I crossed with J, so that's and what did we say? We say I crossed with J will give us what? K, I, J, K. I crossed with J will give us K. So we have 2 10 to the power 6 plus 2 10 to the power 6 times 0.03 K. Okay. All right. Now let's do the J component. So if we do this crossed with this, that 3 10 to the power 6, J crossed with I will give us what? Negative K. So it will give us minus 3 10 to the power 6 times 0.03 K, because J crossed with I will give us minus K. Then I do the last one is J crossed with J will give us 0, so plus 0. Okay, so you end up with minus E times, so here we have so we have 2 times 0.03, that's 0.06, so this is 0.06 10 to the power 6 K, okay, minus 3 times 0.3, that's minus 0.09 10 to the power 6 K, and you can do the multiplication. So 0.06 minus 0.09, that's, so it will be minus E times, so this will be minus 0.03 10 to the power 6 K. Yes. So the distributivity, so you multiply this with this, and I crossed with I is 0, so that's what we have, the first 0. No. Then oh, sorry. This is 015. Thank you. Huh? Yeah. So here we have some. Please follow me because I do make mistakes. I'm going fast. So yeah. Okay. So this is. So that's 2 10 to the power 6 times 0.15, and I crossed with j is k. Okay. So let me correct this. 2 times 0.15. That's 0.3. 0.3 10 to the power 6k, and for the j we did not make a mistake. We multiplied 3 10 to the power 6 times 0.03, so we end up with, so now we correct this. So 0.3 minus 0.09, that's 0.21 10 to the power 6. Okay, and you have to multiply by the negative charge, which is minus 1.6 10 to the minus 19. So you can either do the matrix method. If you have 3 components for the vector, you should use the matrix method. It becomes too long. Or you can use this method, because you know I cross with j will give you k, j cross with k will give you I, and so on. And if you reverse the direction, it gives you minus. If you go in the other direction, for example, if you go I crossed with k, will give you minus j. Okay, j crossed with I will give you minus k, and so on. So you can either use this mathematical method, or you can use the matrix method, whichever is easier for you, and you don't make mistakes. Okay, so here we did the matrix method for the electron, but you can use it also for the proton, and basically the only thing that will change is the sign. So here it's minus 3.36 10 to the minus 14 Newton, and so this is k here, so really we should, yeah, so this is the so it has only component in the k direction. For an electron, if the charge is a proton, it becomes plus 3.36 10 to the minus 14 newtons. Clear? So far is clear. Okay? So let me go to the next one, and let me, all right. So the way we represent the vectors, the magnetic field vectors in problems, we have only 2 choices. Okay, we either represent them as in a Cartesian coordinate like so. So here I'm showing the x, y, and z, and you can draw. So this is a 3-dimensional Cartesian coordinate, and you can draw. So here I'm drawing the velocity vector against the x-axis. The magnetic field vector is in the xy plane, and you can see when you do the cross product between them, you get, with the right-hand rule, you get the force pointing in the minus z direction. But sometimes you might have, these are not in the same order. You might have, for example, this as x, this as y, and usually that's what we use. We use x, the horizontal, y, the vertical, and the one coming out of the page is the z direction. That is the most common representation. So this figure is actually not a good one. I wish I found the figure that has x and y and z, but you have to be careful. In other words, the problem might show you different. So for example, you might have a problem, instead of showing this as x, it shows this as x. So we x, y, and z. All right. So the other way we represent the magnetic field vector is either by a dot. If the magnetic field vector is pointing outside of the page, we represent it with a dot. It's like an arrow coming at you. Remember the arrow. If you look at the arrow coming at you, it has a point and it has a circle around it. In some books they draw a circle also, meaning the arrow is coming at you. And if it's into the page, so coming out of the page, usually we take it to be the positive z-axis. Into the page, so if you look at the arrow from the back, the arrow usually has some wings at the end of the arrow, and so if you look from the back, you will see the arrow has like an X shape, and so on. So if the magnetic field vector is into the page, usually we use that as a negative z direction. So, but just have to be careful. But usually that's what we do. So out of the page is positive z direction, into the page negative z direction, and to the right the x-axis, and upward is the y-axis. Okay, so let me go here. Okay, let's assume we have a positive charge q. Okay, and it's going into magnetic field. The magnetic field, as you can see, it's coming out of the page because we're representing it by B, so it's in the Z direction, in positive Z direction. The velocity in the Y direction, so if I draw the Y-axis, this is my Y-axis here, this is my X-axis here, and this is my positive Z-axis. Okay, so you can see the magnetic field vector is in the positive Z-axis. We said that this charge will experience a force, and the force is given by the right-hand rule. So let me use the curling. So if I bring the first vector V to B, okay, so if I bring V to B, the force is going to be into the page. Yeah? So let's see, sorry. No, V, okay, this is a positive charge. So I bring V into B. See, this is V and B, yeah. So let me use the fingers, okay, instead. So we have V is going up, and B is coming like this. So B is going up. The magnetic field vector is out of the page. The force is pointing in the thumb. So the force is in this direction. Okay, so this is the force here. Now, obviously, if the velocity, now the particle is going to move into a circle, so if it moves into this position, the velocity vector is now going to be like this. The force now is going to be like this. And so on. So if it reaches here, the velocity is like this. And the force is like this. So we notice that this is a centripetal force. Okay, and we are familiar with a centripetal force and uniform circular motion from physics 121. We can write the equations. So let's write the equations for uniform circular motion. The first thing I need to write, the force is equal Q V crossed with B. Okay, and we know this is equal to MA. This is Newton's law, Newton's second law. Okay, so since the magnetic field vector and the velocity vector are perpendicular, I can simplify this. So it becomes, I can write the magnitude of F is the absolute value of the charge Q. Yes, Ibrahim. Something? Okay, so please pay attention. This derivation is very important. If you know how to do this one, you will be able to solve maybe 30% of the problems of this chapter. Okay, so I multiply the absolute value of the charge times the magnitude of the velocity vector times the magnitude of the magnetic field vector. This is equal to the mass times the acceleration. What's the acceleration for uniform circular motion? V squared over R. Thank you. So this is equal to mv squared over R. R is the radius of the circular path. This is R. So now I have this equation, and I can use this equation to solve for anything in this chapter. Oh, well, in this section at least. Okay, so first of all, I can solve for R. So the radius R of the circular path is going to be equal. So first of all, let me cancel the square and the V here. So it's going to be equal to mv divided by qb. This is the first one. Second, I can solve for V. So I can solve for V. Notice we have V squared here and V. So we can write V is equal to Q times B times R divided by M. Second equation. Okay. Now, I know this is uniform circular motion. The velocity on a uniform circular motion, if I want to determine V, I can divide the circumference of a circle divided by the period. V is equal to the circumference of a circle divided by the period. It takes, the period is how long it takes to make a one single revolution, one full circle. So what is the circumference of the circle? It's 2 pi r divided by the period t. So I can get, and let me write V. We know V is equal mv over qb, so this is equal to mv, okay, mv over qb. I can solve for t. Okay, so notice, did I forget something here? So, no, sorry, this is 2 pi r over t. We need to replace r. So this is 2 pi over t, and r, we read, this is r is mv over qb. Okay, so what can I do here? Yeah, I can solve for t. So t is going to be, so I have v here and I have v here, they will cancel. So t is going to be 2 pi m over qb. This is another equation. This is a period. Notice the period does not depend on r, does not depend on r. It only depends on the mass divided by the mass of the charge divided by its charge and the magnetic field strength. I can write the frequency f. Remember, f is the number of revolutions per second. It's 1 over t. So this is going to be equal to qb over 2 pi m. That's another equation. I can also determine the angular speed. Remember, omega is 2 pi f. Okay, it's the number of radians per second. Remember, we have a linear speed. V is a linear speed, and omega is the angular speed. Remember, what is the relationship between omega and v? Do you remember? V is omega r. So you can either use omega is 2 pi f, or v is omega r, يعني omega is v over r. Omega is v over r. V is omega r, or omega is v. Yes, v is omega r. Okay, so I can get the equation. I can write 2 pi f. So let me write it 2 pi f. 2 pi f, so the 2 pi's will cancel. That means omega is going to be equal to b qb divided by m. Another equation. So notice all of these equations, I got them from these. So you don't really need to memorize everything. If you can write Newton's law and you remember F is QVB, you can solve for V, you can solve for R, you can solve for the period T, okay, and so on. This is what we have done here. So here, this is what we just have done. We wrote F is equal QVB and the force is equal MA. The acceleration is V squared over R, and from this we get the radius of the circular path is mv over qb. Okay, then we used in the next slide, okay, we determined since the v is equal to pi r, the circumference divided by the period t, we can solve for t. It becomes 2 pi m over q. Here I'd like to really add absolute value for q, because the period cannot be negative. So if the charge is negative, you don't give me a negative period. So we will put an absolute value for all the q's. Okay? So, and you can solve for the frequency 1 over t and the angular frequency. So notice the period, the frequency, and the angular frequency, they do not depend on the radius. They do not depend on the radius. Kind of strange. Okay, any questions so far? All right, so let me go on presentation mode. This is the mode that anyways. taking forever. Okay, so duplicate slideshow. Okay. All right, so this is what we have already covered. Okay. So we notice that the period does not depend on this, the speed also. So it does not depend on the speed. It does not depend on R. It just depends all particles with the same charge to mass ratio. If it's mass or Q over M or M over Q, if it's the same, they will have the same period. So fast particles they move in a larger circle. However, even though the period is the same, omega is the same, but they can move in a larger circle. So, for example, because we know the radius is mv over qb, so if v is large, the radius has to be large. So the fast particles, they move in a larger circle. So this v here is larger than this v. Okay, so stay with me, please. Okay. All right, so let's go to Kahoot. By the way, let me remind you, I don't want, for the attendance sheet, I don't want a name or a check mark. Please sign. Please sign. Because I'm having a problem where I see a signature one day and a check mark in another day and a name in another day. Please, I said sign in the sign up sheet. Okay? I know for sure in certain classes, I know one is not there and somebody writes his name there. Don't do that, please. This is unethical. من غشنا فليس منا. It's unacceptable. Please don't do that. Okay? So, let me go to the Kahoot. Okay, so let me play the Kahoot. And I want you all to sign in for the Kahoot so I can use it for attendance, but I want you to work together. So then the pin is 605-3493, 605-3493. Please, everybody sign up to the Kahoot. I had a problem yesterday. I marked somebody absent because of the Kahoot, and then she was present, but she did not participate in the Kahoot, or she was not there when I did the Kahoot. Please, everybody participate in the Kahoot because it makes my job much easier. Okay? Yes. Yeah, it will. Please, if you finish the paper, bring it back. Okay, so this is the Kahoot question. Here we have two particles, an electron and a proton. They travel at the same speed, v, in a uniform magnetic field. Which particle follows a smaller circle, the proton or the electron? So which part is in the smaller circle? Okay, so you have only two choices, A or B here. So discuss it with your friend. They have the same speed. The proton is much larger. The mass of the proton is almost 1,000 times the mass of the electron. Okay, so which particle goes in the smaller circle and which particle goes in the larger circle? Well, it's asking for the smaller circle. Ready? Discuss it with your neighbor. The particle that follows a smaller circle, electron or proton. Okay, finished? Yes? Yes, raise your hand if you finished. Raise your hand. Okay, so let me start the Kahoot. So the red is proton and the blue is electron. Which one? Okay. All right. So we have 21 are saying electron, which is correct, and 9 are saying the proton. All right. So let's see how we can determine that. Okay. All right. So for me, I don't memorize the equations. I really don't have enough. So I will write it QVB is equal mv squared over r, okay, and I can get r is equal to mv over qb. Okay, you can see the radius of curvature, the radius of the circle is mv over qb. The electron and the proton, the absolute value of the charge is the same, it's E. The magnetic field is the same. The velocities are the same. What makes the difference? It's the mass. We know the mass of the proton is much larger. It's almost 1,000 times the mass of the electron. Hence, the radius of the proton path, the radius of the proton path is larger than the radius of electron path. So, this is an electron and this is a proton. Correct? Okay. Next question. Let's go back to the Kahoot. Okay, so here, this is the result. We have many who are correct. Okay, what is the travel direction of the electron? So we have determined the smaller circle is that of the electron. How does it travel? Clockwise or counterclockwise? Think, pair, and compare. Think, pair, and compare. Thank you. Amal is here. Is this you write your name for signature? Yeah, please. Okay. All right. Alia al-Mahri. Alia al-Mahri. See, Alia is not here. But somebody wrote her name. هي اللي طلعت. Okay. عائشة المرعى. Okay. Lulua, where is Lulua? Huh? Lulua. واحدة بس طلعت من بدين الحصة. Okay, so here is another case. Lulua. Is Lulua here? Lulua. Lulu, I don't know. It's L-U-L-U-A-H. Luluah. Is she here? Somebody signed for her. Huh? This is cheating. هذا غش. Okay. Okay, so answer the question. Ready? Ready, Jama'ah? Ready? Raise your hand if you're ready. Okay, so I just want the direction, clockwise or counterclockwise. Next. All right, so 3 seconds remaining. All right, so 19 clockwise. حتى الأنصر صورتها لكم. It's clockwise يعني. Hint يعني. Okay, so let's do the right hand rule. Okay, so let's do it different ways. So this is the electron here. The magnetic field is into the board. Okay, so we want to determine whether the velocity is in this direction or in this direction. If it's in this direction, it's clockwise. If it's So in this direction is counterclockwise. Okay? We know the direction of the force. The direction of the force has to be centripetal, and the force has to be pointing downwards. The force on the electron. So now we're going to do, first of all, let's try if the velocity is pointing counterclockwise, to the right, to the left, sorry. Okay? So the velocity vector is pointing to the left here. The magnetic field vector is into the board. Okay? The force is like this. Is this correct? Yeah, we have a negative charge. We have to reverse. Okay? So let's do it the other way. Okay? The velocity vector in this case is this one. Velocity vector is going to the right. The magnetic field vector is the middle finger, is pointing into the ball. The force is up. Since it's a negative charge, I have to invert it. This is correct. This is correct, after you do the right hand rule, because it's a negative charge, you have to invert the direction. So the correct direction is to the right, which is in the clockwise direction. Remember, the trick here is you do the right hand rule, and remember the charge, if it's negative, you have to flip the direction. واضح? Okay. All right, so let's go to the next one. So these are the answers. Electron flows in the clockwise direction, and obviously the proton would be flowing in the opposite direction, in the counterclockwise direction. Let's do this problem. Okay? So this is a very nice experiment. I don't know if you do it here. It's designed to measure the magnitude of the uniform magnetic field. Electrons are accelerated from a rest through a potential difference of 350 volts. So usually what we have an electron gun. You pass current through it, and you have electrons. They are accelerated through a potential difference delta V. So they get a speed here of V. Here they start with zero speed. V initial is 0, and V final, let's call it V final. Okay? Then it goes through a magnetic field. Okay, so it says it enters a uniform magnetic field that is perpendicular to the velocity vector of the electron. So let's assume the velocity vector is like this. Let me use another color. So this is the velocity vector, and the magnetic field vector is perpendicular. Okay, and in this case, so it's into the page. This is an electron, it's into the page. This is a magnetic field vector. Okay, now the electron travels along a curved path because of the magnetic force exerted on them. The radius of the path is measured to be 7.5 centimeters. So we measure this radius r. Okay, what is the magnitude of the magnetic field? Okay, so first of all, we are accelerating the electron through electric field, delta V. Yeah? We have a potential difference, delta V. So first of all, we need to determine what is the velocity it will reach of the electron. What do we do for that? We can use the conservation of energy. We can use K initial 0, and this is K final. Okay, and we can use the fact that delta U, this is U initial and U final. So we can write the conservation of energy, delta K plus delta U is equal to 0, okay, which is 1/2 mv final squared minus 1/2 mv initial squared, which is 0. Okay, let's take delta U to the other side. It's minus delta U, which is minus Q delta V. Okay, so the charge is the minus E, so this becomes E times delta V, and we can solve for the velocity, V final. V final is the charge of the electron times delta V times 2 divided by m square root. So this is the velocity. It will enter the magnetic field with that final velocity. Okay, so now I can use my equations to determine what is the magnetic field. What did we write? We said F is equal, oops. is, okay, we said F is QVB is equal mv squared over r. Okay, and for this we get, so we can get B. So B is just going, the V square, the square will cancel. It's going to be mv over, so this is over over mv over qr. So I have everything. I have the velocity V final. So this is m divided by the charge of the electron, r the radius you are given, you convert it to meters, times v, which is the square root of 2e delta v divided by the mass of the electron. Both of them are the mass of the electron. Mass of the electron is 9.11 10 to the minus 31. Charge is 1.6 10 to the minus 19. You can calculate the magnetic field. Okay, what is the angular speed? The angular speed is omega, and we said is omega is v over r. Okay, since we have v, we can, and we have r, we can determine omega. So v over r, it will be square root of 2e delta v divided by the mass of the electron divided by r. Okay, so, or we can use yeah, I think this is the easiest. Remember, in uniform circular motion, we said v is omega r, s is theta r, s is the arc length if you're given the angle and you're given the radius, and we also said the angular acceleration alpha is ar, the tangential angular acceleration. Remember these, so v is omega, and I usually remember v is the omega r, that, and then that reminds me of everything else. Okay, so that's how we solve this problem. And if you look at the numbers, okay, so we have 1.11 10 to the power 7 meters per second. That's reasonable. It's much lower than the velocity of light, the speed of light. Okay, the magnetic field B is 8.4 10 to the minus 4 Tesla. That's 8.4 that's yeah, 8.4 Gauss. So that's about 10 times the strength of the magnetic field of the Earth. Reasonable. Omega is V over R, and you get 1.5 10 to the power 8 radians per second. Very fast. So the electrons are moving very fast. And what the blue color is because they interact with the xenon gas, I think, xenon gas, that will give it a bluish light. The gas molecules are excited, and when they go back to their ground state, they will emit a bluish light. This is actually a very nice experiment. I wish you have an opportunity to do it, because you have acceleration of an electron through an electric field, you have a movement of an electron in magnetic field, and there are so many important concepts that are covered in this experiment. Okay, now let's assume we have this situation. Okay, so, well, okay, so let's assume we have the magnetic field vector B, okay, and you have a velocity vector v. The velocity vector has two components, one parallel to B and one is perpendicular to B. So if this is the angle phi between the velocity vector and the magnetic field vector, so V parallel is V cosine phi, and V perpendicular is V sine phi. All right, so this parallel component does not generate a magnetic force, لأنه the parallel component is parallel to the B field, and since they are parallel, the cross product is zero. But the perpendicular component produces a magnetic force. Okay, so if we write F is equal QV cross B, and we write the magnitude of F is the Q times V, B sine the angle between them. This is the angle phi. Okay, we can write this is QV sine phi times B. And this here is V perpendicular. Remember, V perpendicular is V sine of phi. V parallel is V cosine phi. So this is the perpendicular component. The perpendicular, in other words, the magnetic force is only due to the perpendicular component of the velocity, the perpendicular to the magnetic field. The parallel component here produces no magnetic force. Now the question is, we know if we have only a perpendicular component, the charge will move in a circular motion because the force is centripetal, it will move in a circle. How about if we have another velocity vector in this direction? How do you think the particle will move? Anybody can guess? Okay, we have a straight line here. I will say the force, the magnetic force, is it going to be zero at any time? No, it's still, so there is a circular motion. Can we also have a linear motion? Because this velocity here is causing the charge to move at a constant velocity in this direction. So, what is the combination of a circular and translation? Yes? Exactly. Thank you, Abdullah. It's helix. So the electron, instead of moving in a perfect circle, it will start moving into helix. Okay, depending on the velocity vector, whether it's the parallel component, whether it's up or down, either it moves up in helix or it moves down in helix. This experiment, you can see that. The nice thing in this experiment, by changing the orientation of the magnetic field, you start, instead of seeing this electron moving in a circle, you start seeing a helix. Very nice experiment. Okay, so this is what you end up with. Instead, so this is in case if you have only the perpendicular component to the magnetic field, the particle will just move in a circular path. Because you have uniform circular motion, the force is perpendicular to the velocity always. But if you have a parallel component, there is no forces acting in this direction. It's just the velocity. Remember Newton's first law: if a particle is moving at a velocity v and the sum of the forces is equal to 0, it will continue to move at a velocity v. Okay? So this remains constant. The magnitude of this also remains constant, but the direction is changing. So the particle will be moving in a helix. And there are certain applications where we actually want the particle to move into helix. Most of the application we will see, the particles, either electrons or protons, they will be moving in a circular path. Okay, so let me finish by speaking about the Allen radiation belts. Okay, the Van Allen radiation belts are caused to cosmic rays. These are usually charged particles coming from outer galaxies and so on. These charged particles, they are trapped in the magnetic field of the Earth. So let's assume this is a proton or an electron, and this is the magnetic field, so it will move into a helix. So depending on the strength, here the magnetic field is stronger than here, so the radius here is smaller and then larger here, but it will go back. And what happens is when these charged particles interact with the atmosphere, they will generate those northern lights. The reason we don't see northern lights in UAE is because the magnetic field line is far from the atmosphere, so the charged particles are not acting with are not interacting with our atmosphere, so we don't see northern lights in UAE. But in the north and the south pole, in the north pole and the south geographic pole, these charged particles are close to the Earth and they interact with the air, with the atmosphere. The colors that we see, the different colors are due to the different atoms or molecules in the atmosphere. Okay, so that's what we call the Van Allen radiation belt. And so when you look at it, So here, if you have electron or a proton interacting with an oxygen atom, it will give a green light. And if it acts with another kind of nitrogen, it will give a different light. That's why we see red, green, blue, and we see so many beautiful colors in the sky. So here with oxygen, it will give green light. With nitrogen, it will give red light, and so on. So hopefully you will have an experience to see, or you will be able to see the northern lights. I will see you tomorrow. We have no quiz tomorrow.